Now, something that will obviously be of interest is the idea of finding the distance between 2 points in R3. So, when we represent the distance between 2 points, say P and Q, we represent it using this absolute value sort of a notation, which simply means the difference between P and Q. And that should sort of make sense, not a big surprise, because back in algebra, when we introduced the idea of absolute values, we always talked about them as being distances. So this notation should actually seem pretty reasonable to begin with. Okay, now consider the distance between 2 points in R2. How can this logically be expanded to R3? Well, if I have in R2 xy axes, and I have a point here and a point here, we know this point says x1, y1, and this is the point x2, y2. Using the idea of the Pythagorean theorem, we can find the distance or the length of this hypotenuse, which is simply the square root of x2 minus x1 squared plus y2 minus y1 squared. That's going to be the distance there. Now, how do we take this idea and expand it to R3? Well, in R3, let me see if I can draw this. Let's see, there's y. Here's my x-axis, y-axis, z-axis. Let me put a box here. Let's see, I'm just going to draw a box in 3 space. And bear with me a little bit, pretend like this is actually a box. My drawing skills have never been all that good. Let's see if I do that, Of course, back here I'm going to have this sort of a thing going on. Yeah, you know, that's actually not too bad, except for I think I need to raise this one just a little bit, because I know what I'm going to need here. Okay, so clean this up just a teeny bit. So say I have a point here and a point here, and I'm looking for this distance. Now I'm going to call this point A, which is going to have coordinates x1, y1, z1. That's the point A. And this I'm going to call point B, which is going to have coordinates x2, y2, z2. That's point B. Now, when I look at this, I have a triangle right here. This is a right triangle. So I know that this distance is going to be equal to the square root of this distance squared plus this distance squared. But when I'm looking at this thing, I can also see that I have another right triangle right here. And this point is going to have coordinates that are equal to x2 and y1 and z1. Okay, so looking at these two different triangles, let me take another color here and identify. Here's one of the triangles that I'm working with. So to find this piece right here, because this is the hypotenuse of this second triangle, I can find that by taking this distance squared and this distance squared. Well, this first distance squared is going to be x2 minus x1 squared plus, see, this piece right here is going to be y2 minus y1 squared. And this will equal, I'm going to call this r squared, which is the hypotenuse for this triangle down here. Now, this hypotenuse is really just the base for the triangle that I'm interested in. And I'm interested in this hypotenuse for this triangle? Well, this distance right here is going to be z2 minus z1. So if I square this and I add it to r squared, that will be, by the Pythagorean theorem, this distance here squared. So I'm going to call this d squared. So when I put all this together, r squared is just this. So when I put all this together, what I get is d, the distance that I'm interested in here, is actually equal to the square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. So in R3, this would be the distance between points A and B. So this is the logical extension from what we did in R2. Now let's show that the function x squared plus y squared plus z squared plus 8x minus 6y plus 2z plus 17 equals 0 is in fact a sphere. And I want to identify the coordinates of the center. Well, what I'm going to do is the exact same sort of thing I would do if we said, hey, this is a circle, and I took out the z's. And the way I'm going to approach that is I'm going to bring my x's together. So I'm going to have x squared, takes care of that one, plus 8x, takes care of that. There's no more x's. I'm going to group those guys. Plus, put my y's together, y squared minus 6y, takes care of those two. Now my z's together, plus z squared plus 2z, takes care of that, equals, and I'm going to take this constant and put it on the other side, negative 17. Now what I would do if this z didn't exist, if this was in R2, is I just simply complete the square. So I'm going to complete the square 1, 2, 3 times. So if I complete the square here, I'll get, see, x squared plus 8x plus 8 over 2 squared. Now, because I add this 8 over 2 squared on the left-hand side, I must also do it on the right-hand side. Well, that's same as 4 squared, right? So over here, I'm going to move this over a little bit. Negative 17, I'm going to add to it. I'm going to leave it as 8 over 2 squared so you can see what's going on. Well, this is going to end up being x plus 4 squared from completing the squared. Plus, I'm going to do the same thing here. Y squared minus 6y plus negative 6 over 2 squared. Well, I need to add that to the right-hand side also. Plus negative 6 over 2 squared. And this is going to end up being y minus 3 squared. And of course, do the exact same thing with z. So this could be z squared plus 2z plus 2 over 2 squared. So of course I need to add 2 over 2 squared to the right-hand side. And this will give me z plus 1 squared. So now there's the equation of my sphere. This is going to be x plus 4 squared plus y minus 3 squared plus z plus 1 squared equals, see, this is negative 17 plus 16. This is 3 squares, that's plus 9. Plus 1 more is 10. Oops. Plus 1. 9 and 1 is 10. So, you can do the arithmetic on that. But there's basically the equation of the sphere. And where's the center? The center is going to be located at negative 4, 3, negative 1. Oh, and what's the radius? Well, I guess we do need to add all this up. This is going to add up to be, what, 9. So this equals 9. Therefore, the radius equals the square root of 9, which is 3. So this is a sphere with radius 3. centered at -4, 3, -1.